Here we're going to examine the limit as xy approaches 0, 0 of xy to the fourth divided by x to the fourth plus y to the fourth. Direct substitution will yield 0 over 0, so we're going to skip past that. We're going to consider the limit along the line y equals x. I say we, but I'd like for you to go ahead and pause the video, and it should be a quick computation, but go ahead and find this limit, please. If we're approaching along y equals x, we can either substitute y by x, or we can substitute all of the instances of x by writing y. I chose the first one. So xy to the fourth becomes x to the fifth, and x to the fourth plus y to the fourth becomes x to the fourth plus x to the fourth. We get x to the fifth over 2x to the fourth. Dividing out x to the fourth gives us the limit as x approaches 0 of x over 2, which is 0. That does not mean that we have a limit, so we're going to try something else. We might consider approaching along the line x equals 1, but that won't work for us. In fact, this would be a big stop right here, because the path that we choose has to contain the point of interest. Since 0, 0 is not on the line x equals 1, that's not a good path to choose. Another path that we could choose, though, is along, for instance, y equals x squared. I'd like for you to, again, pause the video and find the limit along y equals x squared. As you may have just seen, writing x squared everywhere we see y will give us, in the numerator, x times x to the 8th, and the denominator x to the 4th plus x to the 8th. Combining those bases in the numerator, gives us x to the 9th over x to the 4th plus x to the 8th. We can divide out the x to the 4th. We end up with the limit as x approaches 0 of x to the 5th over 1 plus x to the 4th, which is going to yield an answer of 0. We now have two instances of the answer, the limit is 0, and we start to suspect that the limit is 0. But since we have not yet tested along every single path, of which there are an infinite number, we cannot definitively conclude the limit is 0 yet. We will proceed using the squeeze theorem. Referring back to our original expression here, we're looking at the limit as xy approaches 0, 0 of xy to the fourth over x to the fourth plus y to the fourth. Let me write that down for reference. And what I'd like to do is I'd like to build this expression using an inequality, essentially. And so first we note that y to the fourth is less than or equal to x to the fourth plus y to the fourth. And what I'm doing is I'm using a portion of the numerator, y to the fourth, and I'm comparing it with the denominator, x to the fourth plus y to the fourth. I'd like to be able to set up a compound inequality, because remember the squeeze theorem talks about three functions. Well, since y to the fourth is less than or equal to x to the fourth plus y to the fourth for all values of x and y, we note that y to the fourth divided by x to the fourth plus y to the fourth must be less than or equal to 1. We further note that since the numerator is x to the fourth, y to the fourth, and the denominator x to the fourth plus y to the fourth, nothing about this can be negative, and so we actually have an expression in this fraction that is between 0 and 1. We haven't yet built the expression that we were originally considering, though, and we actually aren't going to build it identically, but what we're going to do is multiply all three parts of this inequality by the absolute value of x. We end up with 0 is less than or equal to the absolute value of x times y to the fourth divided by x to the fourth plus y to the fourth, which is less than or equal to the absolute value of x. Now the squeeze theorem is all about limits, and so what we do is we find the limit as xy approaches 0, 0 of 0, and that must be less than or equal to the limit as xy approaches 0, 0 of the absolute value of x times y to the fourth divided by x to the fourth plus y to the fourth, which is less than or equal to the limit as xy approaches 0, 0 of the absolute value of x. Now, both ends of this have a limit of 0. So we are able to squeeze the limit as xy approaches 0, 0 of the absolute value of x times y to the fourth divided by x to the fourth plus y to the fourth between 0 and 0. That means that the limit that we're after is equal to 0. Now the name of this section is Limits and Continuity. We're going to look now at a function g of xy is equal to the natural log of 1 plus x minus y. And we would actually like to know, where is this function continuous? Logarithmic functions are continuous on their domain, and so we consider the domain of this logarithmic function. We must have that 1 plus x minus y is greater than 0, which implies that x minus y is greater than negative 1. So g is continuous on the set of ordered pairs xy such that x minus y is greater than negative 1. I went through this just so you'd know that continuity is what it was before. It means that the function value is equal to its limit value, and that's true for polynomial, radical, rational, trigonometric, log, and exponential functions along their domain. Finally, we're going to compute one more limit. We are in fact instructed to use polar coordinates to find the limit as xy approaches 0, 0 of the quantity of x squared plus y squared times the natural log of x squared plus y squared. We'll note that as xy approaches 0, 0, r approaches 0 from the positive side, r of the polar coordinates, of course. So our limit becomes the limit as r approaches 0 from the positive side of r squared times the natural log of r squared. If we recall the graph of the natural log function, we know that as the argument approaches 0 from the right side, the graph itself approaches the y-axis, but in the fourth quadrant, and so approaches negative infinity. Therefore, this limit would give us 0 times negative infinity, which is indeterminate, and so L'Hopital's rule applies. Before applying L'Hopital's rule, I'm going to algebraically manipulate this. We have the limit as r approaches 0 from the positive side of the natural log of r squared divided by 1 over r squared. Before I take any derivatives, though, I'm going to use the property of logarithms that says that if my argument is r squared, then that squared can become a coefficient of the natural log. Now, applying L'Hopital's rule will give us that we have the limit as r approaches 0 from the positive side of 2 over r divided by negative 2 over r cubed, which simplifies to the limit as r approaches 0 from the positive side of negative r squared, which is equal to 0.